So definition for voltage regulation is, it is defined as change in its terminal voltage when full load is removed, keeping field excitation and speed constant divided by the rated terminal voltage. So we know very well that regulation is given by the term change in the voltage from no load to full load. That is what we have seen in the previous class. In the other words, it is defined as change in its terminal voltage when full load is removed. Full load is removed means it is no load condition, keeping field excitation and speed constant divided by the rated terminal voltage. So whatever definition we are stating here, the same thing we are going to express it using formula, that is a mathematical equation. Percentage regulation is equal to EPH minus VPH divided by VPH into 100. So EPH means what? This is no load voltage minus load voltage. After connecting some load, this is terminal voltage VPH divided by VPH into 100, where EPH is nothing but what? No load induced EMF, and VPH is the rated terminal voltage. So this is the definition for voltage regulation. So in the examination, the question will be like voltage regulation of an alternator, and explain voltage regulation of alternator using EMF or MMF or ZPF method. Any of the method they may ask, but before to that, what they will say, they will ask to write the definition. So the definition for voltage regulation is all these things along with this equation, right? Now we will see the different voltage regulation methods here. Methods of determining the voltage regulation. First one is voltage regulation by EMF method. So here this voltage regulation by EMF method, it is not given directly for you in the laboratory. If you are going to conduct any experiment, it will be not given directly. It will be twisted. Twisted means the name of the experiment will be changed. So sometimes it is called as EMF method, or sometimes it is called as synchronous impedance method, or sometimes it is called as pessimistic method. And later I will tell you why this will be called as synchronous impedance method, or why it is called as pessimistic method. Fine. Now before going to start with the what is that EMF method, let us see what do you mean by open circuit characteristics and short circuit characteristics, because this is also part of your voltage regulation concepts only. So OCC stands for open circuit characteristics, SCC stands for short circuit characteristics. It is one kind of graph. So let us see what is that OCC graph and SCC graph before entering into this EMF MMF method. And to explain that OCC and SCC graph, I am going to take the help of this open circuit test as well as short circuit test pertaining to EMF method. Sometimes in the examination they may ask the question like, explain OCC and SCC characteristics of alternator. Then at that time, what you are supposed to write is this answer. OCC characteristics means what? SCC characteristics means what? OCC means it is the graph of, so OCC, here you can see OCC, it is the graph here. This is y-axis and this is x-axis. So for OCC, y-axis will be voltage E0 in volts, whereas x-axis will be field current IF in amps. So this is open circuit characteristics. Similarly, what do you mean by short circuit characteristics? Short circuit characteristics means this curve. It is this curve. So for short circuit characteristics, here the y-axis, we have to consider this y-axis. So y-axis will be armature current IA in amps, whereas x-axis will be field current IF in amps. So if you are getting confused, means here I will separate the things one by one. So for open circuit characteristics, I will draw the graph here. For open circuit characteristics, the graph will be like, so y-axis, x-axis. So for y-axis, we are going to take no load voltage E0 here. So for y-axis, we are going to take voltage E, and for X-axis we are going to take field current IF. IF stands for field current IF in amps. IF in amps. So now this OCC indicates OCC. It is the graph of change in the voltage for different values of field current excitation. So here we are going to maintain the rated speed of an alternator, and slowly we are going to, and as it is saying, it is OCC means what? Open circuit characteristics. OCC means you have to not connect any load. Alternator should not be connected with any load. Then you have to maintain the rated speed of the alternator, and slowly you have to improve the field excitation. Field excitation means you have to increase the field current. Then as field current increases, then voltage will be keeps on increasing. How long you have to increase the excitation? Till we get rated voltage. And this graph we call it as open circuit characteristics graph, that is OCC. OCC means alternator should not be connected with any load, maintain the rated speed, and change the field excitation. How long we should change the field excitation? Till we get the rated voltage. So this is my rated voltage line. Is it clear? OCC, open circuit characteristics. So y-axis is what is that? No load voltage E0 in volts. X-axis is field current IF in amps. So this OCC will give us what? OCC will give us which value it is going to give us? Yes? OCC gives us which value? Which parameter you are getting here? As I keep on changing the field current, I am going to get E means what? Which parameter it is? Ajay. Which parameter you are going to get? Can you hear my voice?
EMF, sir.
Always open circuit voltage, open circuit characteristics will give us voltage information. Understand that it is going to give us voltage information. So you have to keep on changing the field current IF till we get rated voltage. So why this I? After changing IF we are getting rated voltage? It is very simple. Why? Because voltage is directly proportional to what? E is equal to 4.44 F by TPH KP KD. I hope you remember this formula. E is equal to 4.44 F by TPH KP KD. So from this, which is the constant? 4.44 is constant, frequency is constant, TPH is constant, KP and KD is constant. What is the only variable parameter here? E is directly proportional to what? E is directly proportional to?
Right.
Yes, flux. And this flux, how you are getting? How do you get the flux? By changing which parameter? Flux is given to us by which winding, whether field winding or armature winding? Flux means imaginary lines of force, that is magnetic lines of force. So those magnetic lines of force is given by which winding? Field winding or armature winding? Obviously it is field winding. Remember, it is field winding. So if I want to change the flux, means I want to change the field winding current. So flux is a function of field current. So if we change the field current, you are going to change for the flux value. If flux value is getting changed, then flux is directly proportional to voltage. So the reason behind changing field current here is we are going to change the flux value here. Try to understand. Is it clear why we are changing the field current here? If we change field current is directly proportional to the flux. If flux is getting changed, it is directly changing to the voltage. So initially bring the machine to the rated speed without connecting any load, then slowly keep on increasing the excitation. Excitation means if we are going to increase the excitation means field current we are increasing. If field current is increasing, then field current is directly proportional to the flux. Flux will be changing. If flux is changing, then voltage will be starting to getting developed. So if here we are going to build up the voltage. So this we call it as voltage building curve. So here you are going to build the voltage till rated value by slowly changing the field current or by changing the flux value. Is it clear, all of you? So open circuit characteristics will give us rated voltage value. So if there is no flux, then there is no voltage. This is the meaning. So to develop the voltage, I should have flux. If I want to have flux, I should have excitation, because flux is given to us by the field winding current, that is IF. Is it clear?
Yes, sir.
Yes,
So
sir.
shall I explain SCC now? SCC, short circuit characteristics. So to explain the SCC, so for SCC, it is the graph of SCC stands for short circuit characteristics. So y-axis here now it will be IA on y-axis, and along x-axis once again here so here once again is only. So this is for short circuit characteristics SCC. So now open circuit means what? Here we are not connecting the load, but short circuit means what? If it is a transformer OC or SC test, or open circuit we are not connecting any load on the secondary side of the transformer. And for short circuit test, what we are doing there in case of transformer,
We are connecting
we are
the load.
shorting the secondary side of the terminals, yes or no? Secondary side we are shorting, right? So in the same case, now here in place of transformer you are given with an alternator. For alternator, how to determine short circuit characteristics? SCC means what? Can anybody? Which is the parameter getting during short circuit?
Current.
Whether current or voltage?
Current, sir.
Very good, current. So in short circuit test, you are going to get the full load current, armature current value, that is IASC, short circuit armature current. Full, or otherwise it is IAFL, full load armature current, IAFL, IAFL. Right. So now for short circuit current, for short circuit test, what you have to do is you are given with what is that? Now here you have to keep the excitation minimum. Bring the what is that? Alternator to the rated speed by keeping excitation minimum. This field current should be kept minimum, and you have to short the secondary. What is that? Not secondary side. You have to connect some load here. You have to connect some load, and you have to short it by closing the TPST switch, triple pole single throw switch, and then that current you have to observe it now. So here y-axis is armature current and x-axis is field current. So how long you have to vary the field current?
Up to
How long you have to?
rated current.
Till you get the rated current. Very good. So now here you have remembered that it is very similar to your, what is that? Short circuit test. So here you have to, what is that? Check the ammeter. Earlier here you, to check the voltage for OCC, you are going to note down the rated voltage by using or by observing voltmeter. But for SCC, here we are going to develop the short circuit current by allowing, what is that? By for a small change in the field current by closing the TPS-T switch with some load, and that short circuit current you can observe or you can read with the help of ammeter. So here for one particular field current, you will be getting the, what is that, full load armature current value. Suppose this is my full load armature current value. Yes, can you hear me, all of you? So for one particular field excitation current, you will be getting, suppose this is my full load armature current, and in your laboratory the alternator is having full load current as 3 ampere. So for 3 ampere full load current, for 0.29 field excitation, you will be getting 3 ampere current. So for this field excitation, you will be getting full load armature current. Then what you have to do, just you locate one single point, and from the origin you draw the straight line. So this indicates short circuit characteristics. So short circuit characteristics means it is the graph between armature current versus field current, which gives us the information of full load armature current. And for open circuit test means it is the graph between no load voltage E0 in volts versus field current in amps, which gives us full load voltage information. Is it clear? OCC means voltage information, SCC means current information. For open circuit, don't connect any load. For short circuit, connect the load and short it using TPS-T switch and read that current using ammeter. And for OCC test, don't connect any load, run the alternator to rated speed, and for different values of excitation or field current values, note down the rated voltage value. And that voltage value you can observe it using voltmeter. But in SCC test, you should note down the current value using the ammeter. This is the only difference. So I hope you understood what they mean by open circuit test open circuit characteristics and short circuit characteristics. Do you have any doubts? And in both the cases, x-axis will be what? Field current only. Here also it is field current. Here also it is field current. Is it clear, all of you?
Yes, sir.
So this is all about OCC characteristics. So here in the notes we have written all together. This graph is for OCC. For this graph, let me explain you. For this graph, for OCC, you should consider this blue color line. So this is my OCC. OCC means it is a graph between E0 versus field current IF. So this is OCC. And now to indicate SCC, what we are doing here, instead of taking y-axis on this side, here we have taken that y-axis. So y-axis is what here? As usual, armature current, and x-axis is once again same common field current. So now this is my armature current. So this is what? This is SCC. So instead of taking y-axis on this side, here that y-axis is taken on the other side. For that sake, you may get confused. For that sake only, I have separated OCC and SCC separately. Is it clear? And these are the graphs what you are going to draw while solving the problems based on EMF method as well as MMF or otherwise ZPF method. So these are the common curves which we are going to plot it using the graph while solving the numerical problems related to EMF, MMF or ZPF, as well as in the laboratory these related experiments calculation. Fine. Shall I explain the EMF method now? Do you have any doubts? Shall I proceed to EMF method?
Yes, sir.
Okay. So we'll discuss to the first method of calculation of voltage regulation. Methods of determining voltage regulation. First method is voltage regulation by EMF method. So this EMF method, this is also called as synchronous impedance method or pessimistic method. And later on I will tell you why this will be called as synchronous method or pessimistic method. And in the examination, if you get the experiment based on EMF method, then the question will not be like conductors test on alternator to determine voltage regulation using EMF method. We may ask the question in the other way. We may say that conduct synchronous impedance method of calculation of voltage regulation of alternator. Then you should understand it is EMF method. Or otherwise, we may say that conduct pessimistic method of voltage regulation method to calculate or to determine performance of an alternator. Right. So whether it is pessimistic method or synchronous impedance that is indicated as ZS, if it is there, then you should understand it is EMF method. Is it clear? Okay. So this EMF method or the synchronous impedance method, which we call it as ZS. Synchronous impedance method involves 3 tests. So while conducting the EMF test to determine voltage regulation, here we are having 3 different testing methods. The first method is open circuit test, or if it is open circuit means it is as good as no load. For that sake, we call it as no load test. Second one is short circuit test. Third one is measurement of armature resistance, RA. So here, all these 3 tests will give us certain information which is related to calculate the voltage regulation here. Right. For that sake, these all 3 tests are important for us in EMF method. So let us see how to conduct open circuit test. Right. First one is open circuit test. This is basically a no load test where the alternator is driven at its rated speed. So here, don't connect any load and bring the alternator to its rated speed value, and this speed is kept constant, and you have to keep the speed constant throughout the test. So this speed has to be kept constant and don't allow any load to be connected. Then second step is what? Field excitation. What do you mean by field excitation here? Field excitation means which value? Field excitation means what? Lakshmi.
Field current.
Field excitation means field current. So that is very good. That is IF. Field excitation IF is gradually increased in steps for different values of the field current. So here we have to keep on changing the field excitation value or otherwise field current. And for that corresponding IF, which value is going to be changed, whether current will be changing or voltage will be changing in open circuit test.
Voltage.
Voltage, sir.
Yes. Whether voltage is changing or
Voltage.
current is changing. Voltage is changing, right?
Changing, sir.
So, and corresponding values of no load induced here, and corresponding values of the no load induced EMF are noted down. So you have to note down the corresponding voltage values for different values of field excitation. So this will give us which curve? Whether it gives us OCC curve or ACC curve. Just by looking to these steps, what the thing is here for different values of IF, you have to plot the, what is that? Voltage. So here you will be getting what? OCC curve. Don't connect any load, allow the alternator to run at a constant rated speed, and slowly you change the field excitation. So as field excitation will be changed, flux will be changing. As flux is changing, then voltage is start to build up. So how long you have to vary the excitation till we get the rated voltage. So this is my rated voltage value. So the circuit diagram to conduct open circuit test is this is the circuit diagram where this is my alternator, three phase alternator having three phases R, Y, and B, right? This is the rotor, and here the terminals of the alternator R, Y, B, it is connected to what? Some TPST switch, triple pole single throw switch, and in between that you will be having ammeter. But for open circuit test, this three terminals should not be connected to the TPST switch because it is open circuit test, means this should be kept open. And on the other side, you will be having field winding. This is armature winding of the alternator, and this is field winding of the alternator. So to vary the field current, current can be changed by which element? Whether resistance or capacitance or inductance. Yes? Resistance. Very good. For that sake only here we are connecting one rheostat in series with the field winding, and as you keep on changing the resistance, then you are going to find that field current will be changing, and that change in the field current you are going to observe it with the help of the ammeter, and for excitation purpose here we are using DC supply plus minus for field winding. Is it clear? In your laboratory, to give the power supply to the field winding, we are using rectifier. To convert AC to DC, that DC supply we are going to give it to the field winding, and then you are going to change the rheostat value so that IF will be changing, and that change in the IF value can be noticed with the help of this ammeter. And this is the voltmeter. So this voltmeter gives us no load voltage value E0. Wait a minute. So this will give us, this voltmeter reads VOC or E0 value. So this is E0 or VOC value, whereas this is IF value. This ammeter will read IF value. For different values of IF, note down different voltage values. So these points you will be getting, and later on you have to join the points with the smooth curve. This is nothing but OCC curve. For OCC curve, this should not be, terminals of the alternator should not be connected to the TPST switch, and this armature winding, they are connected in star fashion, and this is the prime mover which will give us mechanical input to the rotor of the alternator. Is it clear? Yes. For different values of the IF, how you are changing? You are changing with the help of rheostat. As rheostat will be varied here, then IF will be changing. As IF will be changing, different voltage you will be getting. So as IF will be changing, different voltage points you will be getting. How long you have to change till you build up the rated voltage, and this is called as OCC. Yes. Field excitation is increased until alternator builds up the rated voltage. Okay. From the data obtained from the no load test, a graph of open circuit voltage per phase against the field current is plotted. That is, we are going to plot E0 versus IF. So we are going to plot E0 versus IF graph, and this graph we call it as OCC curve or magnetization curve. Magnetization curve means IF is nothing but flux value. So for different flux value, you are going to get the voltage value. For this curve, we are going to call it as open circuit curve or open circuit characteristics curve or magnetization curve. Is it clear? This graph is called open circuit characteristics OCC. This is called as OCC. Is it clear how to do the test? Yes. Is it clear how to conduct OCC test? Now we will see the second test in EMF method. The second test is what? Short circuit test. So in the short circuit test, what is the case? The alternator is driven at rated speed on no load. See, so initially alternator is driven at rated speed and that on no load condition. Field excitation is kept minimum. This is very important. So here we are going to keep field excitation at minimum value. Okay, it will be kept at, the field excitation is kept minimum. Close the TPST switch to so that armature terminals are shorted through a low resistance ammeter. The field current is adjusted such that rated current flows through the. Yes.
Sir,
Do you
your
have any
screen
doubts?
is blurred, sir.
Now?
Now it is okay, sir.
Okay. So see that for short circuit test, alternator is driven at rated speed on no load. So alternator is driven at what? Rated speed, and that too on the no load condition. Field excitation is kept minimum. Field excitation means what? IF value is kept minimum. Then close the TPST switch. Then since it is a short circuit test means now here we have to close the TPST switch so that armature terminals are shorted through a low resistance ammeter. So here you have to close the TPST switch so that armature gets shorted with the help of low resistance ammeter. Then what we have to do? Field current is adjusted such that rated current flows through the short circuit armature winding. Now slowly you have to adjust the field current such that short circuit or full load current of the will start to flow through the ammeter, and that full load current is corresponding to the armature winding of an alternator. Okay, the value of the field current which causes the rated current to flow through the SC means short circuit armature winding is noted down. So as soon as you get the rated current value for different for corresponding field current value, that you have to note it down. You have to note down both armature current as well as field current. So for what armature current value I have to note down IF value? You will say, suppose you are changing the field excitation now for a short circuit test. For what particular value you have to note down IA and IF? That is my question.
Up to when we get rated current, sir.
Very good. So once you get the rated current value, so for that corresponding rated armature current, check what is the rated, check what is the field current. So note down both armature current and field current. Just one single point value is enough for us to plot that short circuit characteristics. Okay, based upon this data, the short circuit characteristics, which is graph of IA, means armature current versus IF, is drawn. IA versus IF is drawn. So this is nothing but short circuit characteristics. Okay, both OCC and SCC are plotted on a common field current basis. I told you that for OCC as well as SCC, field current is common along x-axis. So now for short circuit test, the procedure is very simple. So after conducting open circuit test, now we will go for second step, that is short circuit test. For short circuit test, run the alternator for rated speed without load. Initially don't connect any load and run the alternator to the rated speed. Then after that, keeping the field excitation minimum, IF value should be kept 0. Minimum means it is almost 0 only. Then if I want to kept 0 means how this current can be kept 0? Resistance should be maximum. Yes or no? If resistance is high, resistance means rheostat which is in series with the field winding, if this resistance is high, then automatically IF will be low or high?
Low, sir.
IF will be low. So initially don't connect any load, allow your alternator to run at rated speed by keeping the excitation minimum. After that, you have to close the TPST switch of all the 3 terminals. So if you close the TPST switch, now it is what? Short circuit. So here you are going to short it via some low resistance ammeter. And now your work is what? You have to slowly vary the excitation. And you have to check what is my, for this short circuit test. For this short circuit test, here now you have to check what is field current and what is IAS. You have to slowly vary the field current such that this ammeter should be rated current of the alternator. In your laboratory, rated current of the alternator is 3 ampere. So here we are slowly varying the field current such that this ammeter will show 3 ampere. By the time it shows 3 ampere, don't vary the alternator excitation IF value further. Simply you note down what is IF and what is IA. So by the time you get 3 ampere in your laboratory, you are going to check what is IF. Probably you may get IF value in your laboratory is 0.29, which is very low. IF value is very low. Is it clear? So once you get armature, what is that, full load or rated armature current, for that corresponding value, note down what is IF value. And now here you have to plot which curve you have to plot for SCC curve. For SCC curve, y-axis is what? Armature current, and x-axis will once again common field current only. So here you have to slowly vary the excitation till how long you have to vary? Till this ammeter shows rated current. So once it shows rated current, for this field current I may get, this is my rated current. So if this is my full load armature current value, IAFL, so then starting from the origin, just you need to connect to that point. So this is my, this value. Suppose this is 3 ampere, 1 ampere, just by taking your laboratory experiment only. Suppose this is my 3 ampere full load current, means if this is 3 ampere and if this is 0.29, then simply you locate that point. By the time you locate that point, just to draw the linear graph. Linear graph means just to draw the straight line starting from the origin and connect to that point. And now this is your short circuit characteristics, which will give us the information of the rated armature current. And this will give us the information of what? OCC will give us information what? Which information? V rated. Yes, whereas this SCC will give us IA rated value. Is it clear how to conduct OCC and SCC test?
Yes, sir.
Yes. OCC, that is open circuit test is over, short circuit test is over. Then what is the next step now? Measurement of armature resistance. So next you have to measure the armature resistance value. So here this is the armature winding, R phase, armature winding Y phase, armature winding B phase. So here you should measure the resistance of each of the winding. What is the armature resistance of this winding, armature resistance of this? Make sure that all the 3 windings you will be given with, but here what we are doing, you can measure any one of the winding resistance, because that winding, armature winding resistance per phase, that will be the same even for the other 2 also, likewise. Okay, alternator winding. So how to measure that? You will see the circuit diagram here. Step number 3 is measurement of armature resistance per phase. So here you are having 3-phase armature winding, and now here input supply is DC. Plus minus means some battery source you are connecting, and one ammeter will be connected in series and one voltmeter will be connected in series. So after giving some, see here, DC resistance per phase of the armature winding is measured by ammeter and voltmeter methods. So here we are measuring the DC resistance because input is given DC here, and by that you will be getting DC resistance, right? That resistance to measure, I am going to take the help of ammeter and voltmeter. Why we are taking voltmeter? Because R is equal to what? R is equal to voltage by current, right? So if I want to measure armature resistance, I can calculate by with the help of voltage as well as current. So this voltage will be given by this, and I will be given by this ammeter, right? Is it clear? R is equal to V by I. So voltage is given by this voltmeter and current information is given by this ammeter, and here since input is DC, so here we will be getting DC resistance per phase. So now DC resistance per phase of the armature winding is measured by the ammeter and voltmeter method. A small DC current is passed through the two terminals of generator. So here what we are doing is that here we are going to pass some small DC current through the two terminals, okay, of generator, and the voltage across it is noted down. And now here, after passing some small DC current, we are going to note down what is current and what is voltage. So therefore DC resistance of the armature per phase is equal to, here half we are taking. Why? Because how many windings it is connected with? Here how many windings are coming in? Two windings, but I want per phase value. For that sake, here whatever voltage and current information you are having, that is of two windings information, but I want per phase, means here we are taking half. So DC resistance of armature per phase is equal to half into voltmeter reading divided by ammeter reading, voltmeter reading divided by ammeter reading. Okay, but here it is DC resistance, but we want AC resistance. But we want what? But we want AC resistance. For AC resistance, skin effect is taken into account, and AC resistance is 1.2 times of DC resistance. So here, since it is alternator is AC machine, so whatever resistance we have measured now, that is DC resistance. So convert that AC resistance into DC resistance. So if it is AC resistance, means then skin effect will come into picture. What do you mean by skin effect? Have you studied anywhere? Skin effect means if conductor is, cross section of the conductor is given to you, then it shows that charges will be accumulated only on the surface of the conductor. Only on the surface of the conductor charges will be accumulated. So whereas the in-between portion, this can be treated as hollow. All the charges will be accumulated over the surface of the conductor, whereas the in-between conductor area can be treated as hollow. If that is the case, then that effect we call it as skin effect. So yeah, skin effect will be coming into picture when it is a AC circuit concept. So since this is a AC machine, for that sake, now whatever resistance we have measured, convert that DC resistance into AC. For that sake, whatever value will be getting, just you multiply it by 1.2. Okay, 1.2 into DC resistance will give us AC resistance per phase of that armature, and hence resistance per phase of armature is computed or calculated. Okay, from the data obtained by OC and SC test, the OCC and SCC are plotted. So whatever the values we have noted down with the help of ammeter, what is that, IA, IF, VOC for OC and SC as well as SC test, use that data and just to plot the OCC as well as SCC curve or the graph. From these curves, synchronous impedance ZS is computed. So now here see that whatever that OC and SC test we have calculated or conducted, and those values you utilize it to plot the graph of OCC and SCC, and now with the help of that graph you calculate synchronous impedance ZS. I told you that EMF method is also called as synchronous impedance method, because here you will be having or getting the concept of ZS in this method. For that sake, this EMF method is also called as synchronous impedance method ZS. Now we will see how to calculate that ZS. So what is this? This curve from which test we will be getting?
OCC.
OCC. And this curve will be getting from SCC. So OCC means it is a graph of E0 versus IF. Then this is OCC. SCC means it is the graph of y-axis is IA, that is armature current, and x-axis is field current. And this is my what is that, one single point you will be getting from the origin. You are going to draw the graph. So this is OCC and this is SCC. OCC means E0 versus IF. SCC means IA versus IF. So this is my full load armature current. You can see here IASC or ISC for field current. Okay, QR. Similarly, and this is my rated voltage. So OCC gives us voltage information, SCC gives us full load armature current value. Now using this OCC and SCC, we are going to calculate synchronous impedance ZS value. Okay, consider a point on P. Consider a point P. Consider a point P. So this is a point P on the OCC, and let ordinate PQR is drawn. So now after drawing OCC and SCC, just to locate that point P, which is the rated voltage value, from there just to drop the perpendicular. So first point to call it as Q, and whichever it is intersecting with SCC, call it as Q. Initial point is P, next point which is intersecting with SCC, denote it as Q, and next point which is intersecting or meeting with field current, you call it as R, PQR. Okay. Let ordinate PQR be drawn, cutting SCC at Q. Cutting SCC at Q. We have PR no load. So what is this PR? So this whole length PR indicates what? It is the length which is corresponding with OCC, and this point P corresponds to what? Check here. This point P is the rated voltage, yes or no? So this is rated. Point P uses rated voltage value. We have PR, that is no load voltage. No load voltage means it is rated voltage for a field current denoted as. But to get this voltage PR, how much excitation should apply? Excitation means you have to check the x-axis. X-axis means field current IF. So for field excitation OR, I am getting no load induced EMF PR. Is it clear? From the OCC, for field excitation current OR, I am getting rated voltage PR here. We have PR, no load induced EMF, for a field current denoted as OR. While for the same field current OR, short circuit armature current in the machine is QR. So for the same field current OR, now here you can see that for the same field current OR, so current means which curve I should refer? I should refer for SCC, and for SCC this is my full load armature current value. You can see here, this indicates what? ISC for field current, that is equal to QR. So now QR is the full load armature current value. So to get this full load armature current value QR, what is the field current I want? Once again, that is also OR only. Are you getting, all of you? Is it clear? While the same field current OR, short circuit current flowing in the machine is QR. What is the short circuit current flowing now? It is QR. QR is the full load short circuit current value, whereas PR is the rated voltage value, no load induced EMF. So PR indicates no load induced EMF during OCC test for field excitation OR, whereas QR indicates full load armature current during SCC test for the same field current OR only. Is it clear? This PR will be getting for OCC, QR will be getting from SCC. QR means current, full load short circuit current of the armature, whereas PR is nothing but no load induced EMF of the alternator. And both these values you are getting for the same field current, that is OR. OR means x-axis is field current, that is excitation. Is it clear? Yes? Shall I proceed?
Yes, sir.
Okay, now how to calculate ZS? We have synchronous impedance. Synchronous impedance means synchronous impedance. So synchronous impedance, it is denoted as ZS. Synchronous impedance ZS is equal to open circuit voltage divided by short circuit voltage is PR divided by short circuit current, that is SCC information, that is QR. PR by QR. Condition is what? Try to understand. This condition is very important here. Synchronous impedance ZS using OCC and SCC test is given by for the test. What is the common field current here?
I, sir.
No load voltage is PR in OCC, and for same field excitation OR during SCC, the field the armature short circuit current is QR. For these both cases, current is remaining provided the condition is for same field excitation. Okay, so from this graph I can say PR in volts. The synchronous impedance is denoted as ZS. Then open circuit voltage is PR in volts. Then short circuit current. Short circuit current is what here? How much is the short circuit current?
PR.
What is this? QR. PR means voltage. This PR corresponds to open circuit characteristics. Open circuit characteristics means it is voltage information. Try to understand. Short circuit current means you have to check for current, you have to check short circuit characteristics. For voltage, OCC. For current, SCC. So voltage means PR, OCC. Current means QR. QR means which is the point of SCC. Okay. PR in volts divided by QR in amps, ohms per phase. But what is the condition here? Condition is for same field excitation. So what is the same field excitation here? What is the same field excitation? IF is what? IF is OR, yes or no?
Field current.
For both this field current is common. Field current is constant. What is its constant value? From O to R. For this point only I have taken voltage, and for this point only I have taken current. Yes. You have to consider ZS value in this way only. If you take voltage at this point, current at this point, means what is the indication? Suppose you may take current voltage at this point and current at this point. In both whether here condition is what? For same field excitation. For that sake, same field excitation for what is the current voltage, OCC, and for PR by QR for same field current OR. Is it clear? And now, therefore, after substituting those values, you will be getting synchronous impedance ZS. But we know that from the equivalent circuit of alternator, ZS is equal to square root of RA square plus XS square. Okay, since ZS is equal to RA plus JXS. But we know RA. RA from how we have calculated? RA we have calculated in the third step. We have calculated RA, measurement of armature resistance, by connecting some DC source supply, ammeter voltmeter, converting that DC to AC resistance. This is how we have calculated for armature resistance Ra in the third step, and now utilize this Ra value. And also we have calculated ZS value, which is unknown. I know ZS, I know Ra, which is unknown now. The unknown is simply which is the unknown now.
Excess.
Only synchronous reactance Xs is unknown. So therefore, since Ra is known, therefore synchronous reactance Xs is computed as Xs is equal to square root of Zs square minus SCS information for same field excitation IF value. Then Ra is third step armature resistance, that is Ra value. So once you substitute these values, then you'll be getting synchronous reactance Xs value. Now calculate what is EPH because what is regulation formula? Voltage regulation is given by EPH minus VPH divided by VPH into 100. So VPH is already given to us. This will be given for you in the problem statement. The only unknown for us is EPH value. So you have to calculate what is EPH now. So to compute the voltage regulation at load current IA and different power factor cos pi, we know that no load induced EMF is given as EPH or E naught is given by square root of V phase cos pi plus IARE whole square plus V phase sin pi plus or minus IA into XS whole square. This is what we have seen in the previous classes. How to get that EPH value we have derived in the previous class. Yes or no? So E naught or EPH is equal to square root of, here you can take it as VPH or V, both are same. VPH cos pi plus IARE whole square plus V phase sin pi plus or minus IA. If it is connected with lagging power factor, take plus sign. If it is having resistive load, then it. Now my question is, why we are calculating the XS value? Here I know V phase, I know power factor, because for different power factor values, by considering, we are calculating E naught value, which is OCC and SCC. Using OCC and SCC, we are going to compute for ZS. Using this ZS, we are going to compute for XS. But where this XS value you are using? Can anybody? XS value where you are using? XS value you are using in the EPH formula. Understand here. Square root of V phase cos pi plus IRA whole square plus V phase sin pi plus or minus I into XS. Here, whatever that XS value you have calculated, synchronous reactance XS value, here that you are going to substitute it. Is it clear?
Yes, sir.
Yes. So for whatever that ZS RA, using that you will calculate XS, that XS value you are substituting in EPH formula. So by doing this, you will be getting E naught or EPH value. That is V minus VPH divided by VPH. That value, and for this particular, if it is 0, take 0.6, whatever regulation you have calculated for the transformer in the different power factor values. Is it clear? So this is all. And we come to know why it's also called as synchronous impedance method, because here in this case, to estimate XS value, for that sake, the other name for E. No, it is another name of EMF method. So why it is called as EMF method or synchronous impedance method? EMF method or method. Yes. Why it is called as pessimistic method? Still have not came to know. Now let us see what is called as pessimistic method. And that will be coming method. Sometimes the examination.
Sir, your voice is breaking, sir. Not audible.
Till where I have discussed so far? Can anybody? Is there any disturbance? Yes.
Why this is also known as pessimistic method?
Okay. Advantages have I discussed? Have you gone through the advantages while I'm discussing?
No,
Due
sir.
to some network problem, I found that my connection got disconnected. For the and that why it is called as pessimistic method, we'll see in the advantages and disadvantages of synchronous impedance method. Can you hear all of you?
Yes, sir.
Okay, fine. So here in the examination, they may ask sometimes what are the advantages and disadvantages of synchronous impedance method. So the other method, the other name for EMF method is pessimistic method. So that justification you will be getting in this advantage and disadvantage of synchronous impedance method. So let us see the advantages first here. The main advantage of this method is the value of the synchronous impedance ZS for any loading condition can be calculated. For any loading condition or for any power factor condition, you will be calculating ZS value, right? So with the hence regulation of alternator at any load condition and any load power factor can be determined. So here for any assumed load or for any assumed power factor condition, you will calculate voltage regulation, which is the best part of EMF method. That is the advantage of EMF method. Actual load need not to be connected to alternator, and hence method can be used for very high capacity alternators. So here we are not connecting any load, simply we are assuming the load, and by assuming different power factor condition of the load by different loading condition, here we are going to estimate the voltage regulation. For that sake, this method is very useful for high capacity. Sir? Yes.
Please present the screen.
Screen is not. Wait a minute. Now, can you see the screen? Yes?
Yes, sir.
Okay, fine. So, for any loading condition or for any power factor condition, you can calculate the, what is that? You can calculate voltage regulation. That is the best part of your EMF method. Then, what is the limitation? The main limitation of this method is that method gives large values of synchronous reactance. So this method gives us high value of excess. This leads to the high value of regulation than the actual value of the results. Hence the method is called as pessimistic method. So whatever voltage regulation values you will be getting at the end, these regulation values are too high. Regulation values are too high. Why we are getting very high values is because here this excess value, whatever we are calculating, excess is equal to square root of ZS square minus RS square. This excess value are getting very high here. If excess is high, then excess value are substituting in E naught or EPH value. So if excess is high, then automatically IA into excess is very high. If drop is high, means what about EPH? It will be
high.
Sometimes low, high, sometimes low on type of the load. So this will disturb for excess. Since we are getting very high in EMF method, then this is going to disturb to the IA into excess, which is further going to disturb to the E naught. So altogether, the regulation value, whatever you are calculating with the help of this excess, which is directly disturbing to this regulation value, this will give us very high regulation value. So this high excess value will give us high regulation value. So now, since we are getting regulation value more than the actual value, suppose if the actual value is 30%, then with the help of this EMF method, you may get it as 60%, 70%, which is very, very high than the actual value. For that reason, this EMF method is called as pessimistic method. Is it clear why it is called as pessimistic method? Disadvantage of this method is that method gives large values of synchronous reactance. Excess value is very high here. This leads to high value of percentage regulation than the actual results. Hence the method is called as pessimistic method. It is given as pessimistic method. Is it clear?
Yes,
okay, then let us see why this excess value is very high. Why we are getting high excess value. Okay, synchronous impedance is practically variable. So usually synchronous impedance means what? ZS value. It is variable in nature. Synchronous impedance is practically variable and is not constant. It is not a constant, but it is a variable. If there is saturation, it remains constant. But if the alternator is in the saturation condition, that field winding is in saturation condition, then it is constant. But it decreases towards the saturation. See here, it is going to decrease towards the saturation. Saturation means what? By the time your voltage becomes almost rated voltage value, OCC, if you take This is OCC and this is field current. And this is your E naught. And for SCC, you should draw it from the origin here. Okay, so this is SCC. Okay, if there is saturation, it remains constant, but it decreases towards the saturation. So here IF will be decreasing towards the saturation. And it is for low saturation region. So IF will be keeps on increasing. So IF is increasing for low saturation. Low saturation means this starting point. Starting point is low here. In synchronous impedance method, in short circuit test, the field current required is very small. The alternator is showing full load current how much? 3 ampere. To get that 3 ampere, the field what we so you tell me in our laboratory 0.29 is the field current to get armature current 3 ampere. So whether 0.29 is high or 3 ampere is high? 3 ampere is high, but what is that 3 value? 3 is full load armature current value and 0.29 is 0.29 is what? That is field current value. So field current is very, very small to get full load armature current 3 ampere, right? So simply 0.29 field current is very, and that 0.29 means what? It is very small field current value. It is very small field current value which is given full load armature current and saturation, and it increases for low saturation. Increases for low saturation. Low saturation indicates what? 0.29 ampere current. If you take your laboratory experiment, just for 0.29 ampere, it is very low saturation point. But here the value of ZS is what? Increasing. ZS is increasing for low saturation. 0.29 saturation, ZS is increasing. If ZS is increasing, then what is the thing? If ZS increases, then automatically, if ZS increases, then automatically XS will increase. If XS will increase, then IA into XS will increase. This will affect to the E naught. This will affect to the regulation. Because of that, you are getting a regulation value more than the actual value, which is called as pessimistic method. In synchronous impedance method, in short circuit test, the current required is very small to pass to the short circuit current. Hence, the flux density is low and the region is low saturation region. Hence, the synchronous impedance is much higher than its normal value. Thus, the drop IA into ZS is high, due to which regulation is also high than the actual value by synchronous impedance method. Hence, the method is called pessimistic. So, usually in the short circuit test, we are getting full load armature current for very small value of the field current value, which is low saturation region. And for the low saturation region, synchronous impedance ZS will be keeps on increasing, and that will be constant when it reaches to the linear saturation zone. But since 0.29, if you take your laboratory experiment, that is very small field current value. For small saturation, what is that? For low saturation region, ZS is characterized by high value. If ZS is high, then XS is high. If XS is high, IA into XS will be high, and that will reflect onto the EPH value. Because of the EPH value, what we are using in the regulation values, automatically you will be getting more regulation value, high regulation value than the actual result value. So if you get regulation value high, is it a good thing or bad thing?
Bad, sir.
It is undesirable. It should not happen like that. Yes or no? So this EMF method is not giving us the actual value. It is giving the value which is higher than the actual value of voltage regulation. Is it clear, all of you?